In this video, we're going to learn how to do mole-to-mole conversions. Now, one of the things we really need to make sure is that our equation is balanced, and whether or not you've learned how to balance our equations, you may learn that in the future, or you may have already learned it. You need to make sure that you have a balanced equation. Now, in the first few examples, we have been provided, or we already have a balanced equation, and then the last couple examples I'll do together, I'll actually write out and just show you how you would create your balanced equation to be able to go through and balance these out and to do the conversion of mole to mole. And so I'm going to do a couple on this page that are starred, and I apologize for the not as clear print as possible. It was the only copy I could find of the sheet I've been using in the past. And so when we look at this, it says given the reaction 4NH3 plus 5O2 yields 4NO plus 6H2O, what is the maximum number of moles of H2O that can be produced when 2 moles of NH3 are completely reacted? So what we need to do, there's a couple things. We need to highlight and only pull out the pieces that we need. There's certain information that we need, and then there's certain information that has nothing to do with the question that is being asked, so we can kind of eliminate those. So I want to know, my question is, what am I trying to find? I want to know what's the number of moles of water. So that means I need to know the water piece. It says that can be produced when 2 moles of NH3 are completely reacted. So I need to know the NH3 piece. So because I'm using NH3 and H2O, those are the 2 pieces I'm going to highlight. The other 2 pieces become basically extraneous. I don't really need to know them anymore, and I don't really need to pay attention to them anymore. And so what we need to do is we need to go with what we know first, okay? Go with what we know. What we know first is that there's 2 moles of NH3. Yes, I have a balanced equation, but when I'm trying to find out something else, I need to go with what I know. What I know, there are 2.0 moles of NH3. Okay, that's what I know with certainty, that there's 2.0 moles of NH3 that was given. I want to know how much water, what's the maximum number of moles of water I can create. All we need to do is set up a proportion and multiply by that proportion so that I solve and convert to water, or convert to whatever I'm trying to solve for, and being able to eliminate in converting from the original material. So because I have NH3 on the top, or what I'm starting with is NH3, what I want to do is set up a proportion where I can get rid of and cancel or factor out the NH3. So in this equation, 4 molecules, or because we're dealing with moles, 4 moles of NH3 are going to react and produce 6 moles of water, H2O. So for every 4 moles of NH3, I always get 6 moles of water, assuming I have a balanced equation, and that's what we want, a balanced equation. All I need to do is take my values. I can cancel out my moles of NH3. I'm not canceling any numbers out yet, just canceling out my moles. So I'm going to end up with moles of water. Now I have 2 times 6, which of course is 12, divided by 4, which ends up being 3 moles of H2O. Okay, that's one way to do it. Now, another way to do it, in math class, you kind of set proportions, is over of, and things like that. We could set, for example, 2 moles of NH3 is to X as 4 moles of NH3 is to 6 moles of H2O. And what we get now is a very similar idea, but instead now we've set the proportion equal, we're going to cross multiply and then divide. We would get, for example, all this over, if we just look at the math and not worry about the symbols, 2 times 12 again is 6 divided, we would have 2 times 12 is 6, and then that equals 4x. We would have to divide by 4, and then 12 divided by 4 again is 3. So there's really 2 ways you can do it. I like to teach this way to set up and show the canceling out. If you're in New York State Regents, you can actually show, basically if you show either or, the state will typically give you credit. Okay, but this is the one you typically see when we talk about factoring out or converting from one to another. This would be the better one, and that's the one that I typically teach. So that's the one I'm going to stick with here. But again, you may find it easier just to set a proportion. But we want to show the work. A lot of you might have been able to solve that in your head. The key thing is showing the work when you actually get to it. All right, the next one. We have 2 KClO3s in solid form that will decompose to form KCl, solid, and oxygen gas will be given off. What's the total number of moles of KClO3 needed to produce 6 moles? Now, if we look at the beginning, these numbers, I have 2 moles, 2 moles, and a 3 mole. So that's a 2 to 2 to 3 ratio when we're talking about these. And I can consider a 2 to 2 ratio here. I can consider the 2 to 3 ratio between the first and the ending. You can really consider any of the ratios when you're doing that. So when we look at this next question, if I know 6 moles of oxygen, I want to know how many moles of KClO3. Again, I want to highlight, I'm looking at KClO3 and I'm looking at oxygen. Only focus on the 2 pieces that you need to know. The rest become kind of extraneous. So again, go with what we know first. I know 6 moles of O2. I know that first. So that means I want to eliminate oxygen. So my 3 moles from the original equation are going to be on the bottom, and my other value will be on the top, which again is in the original balanced equation, 2 moles of KClO3. And again, my moles cancel out, and I will be then converted to KClO3. 6 times 2 is 12, divided by 3, we get 4 moles of KClO3. That's how many moles I would need in order to get this. And again, if we look at it as a proportion, just in your head, I know that 2 is equal to 3. Every 2 I have here will give me 3. So if I were to, if I wanted 6, if I wanted twice as much, then I need twice as much to start. If I want to finish with twice as much, if I wanted to finish with 6, then I would need to start with twice as much. So some of it becomes common sense when you're going to check your math and see if your math is correct. But again, we want to go with what we know first, then we want to set up our proportion and factor out, and then we can have our final answer. And so we'll do one more on this page, and then we'll get to the back. We'll do another one over there, and then we'll get to some where we actually have to create the formula itself. Okay, so we have aluminum plus sulfuric acid, 3 sulfuric acids, gives us hydrogen, 3 hydrogens, and aluminum sulfate, Al2SO4, 3 times. The total number of moles of H2SO4 needed to react completely with 5 moles of Al. So I'm talking about moles of aluminum, so there's my piece of aluminum, and I'm talking about H2SO4, so there's my H2SO4. We don't need to worry about the other 2 because the question doesn't say anything else about hydrogen, doesn't say anything else about Al2SO4. The only thing it's talking about is aluminum and sulfuric acid. Now, I already know there is a 2 to 3 ratio. So for every 2 of these, I need 3 of these in order for it to react. So the question says, what's the total number of moles of this if I'm going to use 5? Now, maybe in your head it's not quick and easy to say, okay, to go from 2 to 5 isn't as easy as just going from 2 to 4 and doubling. But some of you might be able to do that in your head. It can be a proportion. But we want to go with what we know. So we have 5 moles of Al. So that's what I know for certain. And I want to know H2SO4. So I know in my proportion 2 moles of Al is on the bottom because I want to cancel that out. And I'm going to convert to H2SO4, 3 moles of H2SO4. My moles of aluminum cancel out. 5 times 3 is 15, divided by 2, 7.5 moles of H2SO4. And if you wanted to round that up, okay, depending on what you're working on, you could round it up to 8, but technically we would want to leave it as the best answer, especially because my original value, if you're doing significant figures, this one has 2 significant figures. So my answer should have 2 significant figures, 7.5. All right, a couple on the back, and I want to deal and mention the idea that sometimes you see them where they don't have the equation and you need to actually come up with your own balanced equation. So let's take a couple, look at a couple here. So for example, iron will react with oxygen to produce Fe2O3. How many moles of Fe2O3 will be produced if 0.18 moles of Fe react? So iron reacts with oxygen, Fe plus O goes to Fe2O3. Now we need to remember a few things. We need to remember, first of all, that oxygen is one of our diatomic elements. That means it's always as a 2 value, or it's always bonded to another atom of the same element when it's in its pure form. So oxygen is always O2, and you might have learned about the Hofbrinkels okay, HOFBRINCl, the Hofbrinkels, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, those are all diatomic. So anytime they're pure or by themselves, they're going to be with a 2. Now, when we look at my formula, I'm not balanced. I have 1 iron here and I have 2 irons there. I have 2 oxygens here and I have 3 here. So balancing equations sometimes can be a guessing game, but there is, of course, math involved. And a lot of times you want to find common denominators or common values that each of them will go into. And so, for example, if I have something that's by itself, I can add any number here, save that to the end, try to balance the other ones off first. I have 2 over here and I have a 3 over there. The only thing that 2 and 3 both match up to try to keep the smallest proportions is gonna be the number 6, okay? I can put a 3 in front of this, and now 3 times 2 makes 6 oxygens. If I put a 2 in front of the whole molecule here, and if I expand 2 times 3, that also makes 6 oxygens. But what that does now, we also have to expand this. That means I have 4 oxygens. I can put a 4 here. So now I've actually created my ratio. My ratio is 4 to 3 to 2. Again, when we do these, the ratio is the number that comes in front. That's your whole number coefficient when you have your balanced equation that's going to help make the equation balanced. So now I can go back and look at the original question. How many moles of Fe2O3, so we're looking at Fe2O3, will be produced if 0.18 moles of Fe react? So I go with what I know. 0.18 moles of Fe, and I want to know how much Fe2O3 will be produced. So again, I'm trying to solve Fe2O3. I know that there's 2 moles of Fe2O3 for every 4 moles of Fe. That was for my original equation. Again, the one I want to get rid of is on the bottom. The one I want to solve has to be on the top. So my moles of Fe are going to cancel out. We get 0.18 times 2 divided by 4. Now again, just in if you want to use your calculator, you would just enter 0.18 times 2 divided by 4. But if we think about the math, really 2 over 4 is really 1 over 2. So we're multiplying this and we're basically dividing it by 2 or multiplying it by 1/2. And so our final answer is 0.09, and that would be moles of Fe2O3. And so again, we went through and actually created a balanced equation. So we'll do one more balanced equation, and then hopefully by this time you'll have grasped the concept of how to do, again, these are mole to mole conversion problems. How to convert from moles to moles. Now, there's other conversions. You can convert from mass to moles, you can convert from particles to moles, you can convert from volume to moles, or you can do the reverse. You can do moles to volume, moles to particles, moles to mass. And so we're just sticking moles to moles. This is probably the simplest and easiest one because it's based on a balanced equation. All right, lead will react with hydrochloric acid to produce lead 2 chloride and hydrogen. How many moles of hydrochloric acid are needed to completely react with 0.36 moles of lead? So again, we need to do our equation. Lead is Pb, and it makes hydrochloric acid, HCl, reacts with HCl and produces lead 2 chloride, PbCl, and we're going to use the +2. So again, when we do the crisscross method, if you remember, the +2, chlorine's -1, when those numbers crisscross, that formula is PbCl2. So I'm just going to get rid of those charges, because in your balanced equation you don't have charges. And we also have hydrogen. So if we remember just from what I talked about a few minutes ago with the Hofbrinkels, hydrogen is one of our Hofbrinkels. It is a diatomic element, so it's always going to be H2. Now when we look at the balanced equation, I have 1 lead, that's balanced, but I only have 1 hydrogen and 1 chlorine, but I have 2 over here. So easily I can put a 2 in front, and now this is balanced because I have 2 hydrogens now and 2 chlorines. So I want to know, I'm dealing with hydrochloric acid and I'm dealing with moles of lead. So I'm dealing with the hydrochloric acid. How many moles of hydrochloric acid are needed if I react with 0.36 moles of lead? Now right now I know it's a 1 to 2 ratio. Okay, so twice as much hydrochloric acid is needed. So when we think about that, okay, maybe in your head you can figure out, okay, if there's twice as much needed, I can just look at that number and multiply it by 2. But if we want to show the actual value, especially to set it up to show your work for New York State, you want to have the correct setup. Again, we go with what we know. So we know 0.36 moles of lead, Pb, and I know that it is a 2 mole HCl to 1 mole of lead, 2 to 1 ratio. My moles cancel out, moles of lead cancel out, and then we get 0.36, and again, there's our times 2. It's twice as much. 0.36 times 2, we get 0.72 moles of HCl are required, and that would be our final answer. So again, hopefully you found value in calculating mole to mole. It should be relatively straightforward. If you notice, the setup is the same every single time. I started with what I knew, and I had my ratio. If you look back here, I started with what I knew, and I have a ratio. If you look at any of those on the back, I started with the number that was in the question, and I set up my ratio or my proportion. I started with the number that was in the question, and I have my proportion. So the setup is the same every single time, and hopefully that helps you with this part of chemistry. And if you have any questions or comments, please leave them below, and I look forward to hearing about your success with massive chemistry and stoichiometry.